So my ambition now is to, that when you leave the room after my presentation, you will understand what immuno-oncology is and how it works, and what change and the impact it will have on the way that we treat cancer patients. And then I will also say a little bit about my company at the end, almost as an example of what I'm explaining to you. I will start with explaining some basics on the immune system, because immuno-oncology is more about immunology than it is oncology. And if you look here, I made an emphasis on you need a balanced immune system. The immune system, if you think about it, what you associate with the immune system is the ability of the body to recognize a foreign intruder and protect you against something foreign trying to come into your body and hurt you. And indeed, that's what the immune system does. And the immune system is very powerful at doing it. It might, in some instances, even be too powerful. If the immune system overreacts to a foreign thing that comes into your body, that's what you call an allergy. If the immune system overreacts to something that's a part of your body, that's what you call autoimmune disease. That's rheumatoid arthritis, type 1 diabetes, and many other diseases. So the point is, these immune responses, they need to be balanced. And they have inherent checkpoints in them that check and balance that the immune system is modulated. So it does the job it's supposed to do, but don't overdo it. That's very important to remember when I come back to the interaction between the immune system and cancer and how we manipulate the immune system to treat cancer. Then, over to cancer. Cancer is a genetic disease. It's always a mutation or many mutations in a cell that gives the cells new ways of behaving. And if those new ways of behaving is leading towards giving the cell, mutated cell, abilities to be a cancer cell, for example, it can divide endless number of times, it escapes the normal control systems for division and growth in the body, then it can evolve into a cancer. And not to scare you, but just the fact, you get these cells, mutated cells in your body many times every day. Everyone does that. And they are cleared by the immune system. And they are cleared by repair mechanisms that are inherent in the body. But sometimes it happens that the cell settles down somewhere in your body and it starts to divide and it starts to grow into a tumor and it develops into being a very serious disease. Immunotherapy of cancer is, like I said, is manipulating the immune system to recognize and kill cancer cells. And this circle here, I'm going to spend some time on it and go through it in quite detail. Understanding this cycle is basically the understanding of immunotherapy of cancer. And when explaining, I'll have to start somewhere. And I'll start here. And the reason why is that this is where my company comes in. This is where we are manipulating the immune system. This green thing here with the spikes on it, that's a dendritic cell, also called an antigen-presenting cell, also called a Langerhans cell. The function of this cell is being the intelligence system of the immune system. It's able to recognize something coming into the body as foreign and respond to it. This is foreign. Understands that this is foreign, it's not good for the body. You have most of these cells located in your skin and in the mucous membranes that lines your gut and in your lungs and here. And that's, of course, that's where they need to be. That's where the foreign material comes in, through your skin. Okay. Anyways, these red dots here, they are the foreign material, or antigens. When the dendritic cell is exposed to these, they pick them up, internalize them, and they travel in the lymph system down to the first and best lymph node they come to. And there, they will start to activate T cells, these blue ones here. They present, that's why they call antigen-presenting cells, they present the antigen to the T cells. And if the T cells agree, they will start to expand, and you will have a lot of T cells directed towards the antigen that was presented to them. If that antigen is a cancer antigen, you have in your body then many T cells able to recognize and kill cancer cells. Okay? Then you go out into the blood vessels, and these activated T cells, they traffic around in your body looking for what they're directed towards. They're looking for the antigen that they started with. And then they come out, they will leave the blood vessel, and here they travel into what is a tumor. And it comes into the tumor, and here you see the T cell, and you see the red dot, the antigen, and here you see the cancer cell with the antigen here, and the T cell connects. Then there is a checking going on if it's advisable or correct for the T cell to kill the cancer cell or not. And this is where these checks and balances and the modulation of the immune response comes in. And if so happens that the, let's say the T cell here gets the acceptance, it will kill the cancer cell. Then a lot of dead material and debris, and mind you, very important, new antigens come out from the cancer cell. And these new antigens, they are picked up by the dendritic cell, and the cycle starts spinning. And if this cycle has started, it does not necessarily need any external maintenance. It goes by itself. It goes round and round and round, and that means that the patient will get an effect from their cancer treatment. So this looks like it's happening by itself in the body. And in some instances, it does. But in most, it does not happen. And that's where immuno-oncology come in. Then you do the following. I said this checkpoint down here, where the T cell and the cancer cell sort of has an interplay, and the cancer cell sends don't kill me signals to the T cell. You can block that system with PD-1 or PD-L1 inhibitors. Then you sort of let loose. You downplay the modulation of the immune system, and the T cells, activated T cells, they get the upper hand, and they are able to kill the cell because this was blocked by a PD-1 or PD-L1 inhibitor. And they are on the market now. They're in clinical use, and they're being developed for a lot more, but I'll talk more about that later. Then another way that you can manipulate this is up here. And this was actually the first treatment in immuno-oncology that was approved for use in humans. That's ipilimumab or Yervoy from Bristol-Myers Squibb. Up here, there is also a modulation, making sure that you don't get too many T cells, because if that happens, you get autoimmune disease, you get colitis, and you get other diseases. So when you block this here, you get a huge expansion of T cells, which is very good for you to fight the cancer, but the side effects are, for example, colitis and autoimmune disease. Those are the side effects of these treatments. Then you have other treatments. You can take T cells or other cells out of the bloodstream, and you can manipulate them in the lab, and you can expand them to large clones, and you can make them artificial. You can make them really good at recognizing and killing cancer cells in the lab. And then you inject them back into the patient. And the speaker coming after me, he's going to talk about how they produce and how they improve the production of these T cells, because it sounds complicated, and believe me, it is. But I understand you can automate it. Another way of doing it is here. And this is where my company is working. Because if you look down here, if you block down here, the patient is totally dependent on having activated T cells against the cancer in the first place. And about 20 to 30% of patients, they have that by themselves. It's endogenous. It just happens in their body. The immune system responds to the cancer, but is unable to kill the cancer cells because of the action of the PD-1, PD-L1 interaction. But they still, those 7 or 8 out of 10 that don't get an effect of PD-1 or PD-L1 blocking, they cannot get it because they don't have any activated T cells. And then, of course, the obvious thing to do is to come in with vaccine and provide activation of T cells for the patients that didn't have it by themselves. And if you look at the result from the clinical trial and also the observations of the use of these medications, you will see exactly that. Well, some other things also I need to say first. All the traditional ways of treating cancer have implications for the immune system. You know, it's like chemotherapy, radiation, you know, we get a lot of debris and antigens coming out here. Oncolytic virus, you know, you basically give the cancer a virus infection while the rest of the body goes clear. You also get the same thing. You get all these antigens out. Then you have the same with target, including cytotoxic monoclonal antibodies and anti-angiogenic treatments. All these have effect on the immune system. But mind you, if you look at it, they're all directed and aiming directly on the cancer cell, while all these other ones here, they are not directed towards the cancer cells. They are directed towards the immune system. And that's the difference. Okay. I will start with this curve here. This is the 10-year survival curve for melanoma patients treated with ipilimumab. And if you look here, it goes down and it comes down to between 20 and 30%, like I said. If you have survived on ipilimumab treatment for 3 years, you're home safe. You will not die from your cancer. Your cancer has become a chronic disease that you will live with, but you won't die from it. It's not going to kill you anymore. And those here, these patients, they are the ones that had activated T cells in the first place, and the other ones didn't. So what we're working with now is, this is the old, you know, the way that the generic survival curves for patients on different treatments. This is chemotherapy or targeted therapies. You do get a life extension, but as you know, if you get cancer, you get a treatment, you get better, the tumor shrinks, and then you relapse after a few years. Then you get a new treatment, and you have first line, second line, third line. But eventually, all these patients, they die at some point. The new thing with immunotherapy is that some patients get this long-term benefit, and their cancer is basically turned into a chronic disease. But it's too few. It's like 20 to 30%. Then when combining different treatment modalities in immunotherapy, you can lift this. And this is the race that's going on at the moment. What do you combine with? And finding smart combinations and doing, the whole point is that everyone, they get sort of the same effect. They get this cycle running. The point of doing combination is to make more patients get into that. Yes, question?
With the combination treatment, how does the FDA treat it?
Question about how the FDA treats the combination treatments. Short story, they love it. Yeah. I say the FDA is, we're in the process now with the FDA in the US, and what you can say is that they are extremely positive. My experience from before is that they're sort of being very careful. They don't want to do anything dangerous like that, but now they are sort of encouraging these combinations to come in. And the thing there is that, you know, when you do these combinations, what's the rationale for a single combination? And I think that's sort of complicated, because if you look at the big pharma companies, the best indication for doing the rationale behind doing a combinations is that you own both drugs. There's no science in it, and they're basically trying and testing anything that they can combine with. This is just to show you all the different tumors. And mind you, it says here, it says tumor site. It does not say cancer type, because This is no longer, I mean, you don't care whether the tumor sits in the lung or it sits in the bladder or your lungs. That's irrelevant. This is biology, not geographical location. Okay? So if you look down here, there's one down here. It says microsatellite instability high. And that certainly is not a tumor site. That's a biological property of the cancer cells. And this is the first time ever that the FDA has approved and given indication on biology only, does not care where in the body that tumor sits, as long as it's microsatellite unstable. Okay, but if you look here, all the principles that I explained to you, I didn't say anything about cancer type. I said cancer. These treatment principles are general. They can be applied to all cancers. And that's what they do. Melanoma, lung cancer, kidney, Hodgkin, head and neck, urothelial, you name it. And these are just the ones that came in now the last 2 years. And this will explode, and it will be, used on basically all cancers. All these here, this one is a CTLA-4 inhibitor working up here. All the rest down here, all those are, all the rest, they are working down here. They are PD-1, PD-L1 blockers. Okay, I'll say something about the long-term forecast. I'll say the short first, and that's very simple. There will be more combinations in more cancers, and more patients will get effect from it. And this is where the big drive is in oncology. This is where it's going, because there's one other thing, and that is the problem with previous cancer treatments targeting the cancer cells is that the cancer cells change. Or rather, also, a tumor consists of billions of cells, and these cells are not all alike. Some of them have properties. They are resistant towards the treatment in the first place. There are so few of them that you can't see them. But when all the other ones are gone, killed by the treatment, they pop up, and they become your new cancer, which is resistant. It's not only an adaptation, but they're there in the first place. And I say, just to illustrate that, I'm going to quote Bert Fogelstein. He held a brilliant speech at AACR, American Association of Cancer Research, just a few weeks ago. He started his introduction, his speech, with saying, I can treat any kind of cancer if you are a mouse. And why is that? Yeah, this is just a numbers game. If you have a metastasis in your liver, that metastasis is bigger than the whole mouse. And if you take the tiny little cancer inside a mouse, it's so small, there are so fewer cells. The probability of having 1 or 2 or 3 resistant cells in that small tumor is very high. While in a human, it's most likely there is resistance there already. So it's just a numbers game, just the size of the tumor and the number of cancer cells.
Which of the combination you're going to do is based on like a genetic test of the tumor or something?
The question is, what's your rationale for choosing a combination? We will get there, because we have now, there's been a development, a lot of biomarkers. You can go in, take a biopsy of the tumor, look at the biopsy. If there's basically not one single T cell in the tumor in the first place, it's what we call a cold tumor. And if you then go in with a checkpoint inhibitor, either ipilimumab in the lymph nodes or PD-1, PD-L1 in the tumor, nothing happens, because there is nothing there to do it. So you have to prime the tumor. You have to make the tumor go from cold to hot. If you, in the first place, go in and you take a biopsy and you see there's a huge influx and there are T cells all over in the tumor, you basically know that you will get an effect of a PD-L1 inhibitor. Or if you go in and you look at the expression, how many PD-L1 receptors do they have in the tumor in the first place? And it's high number, we know that then you have a more likelihood of getting effect of the PD-1 blocking. So in the future, these combinations will not be the same for all patients. You will look for biomarkers, you will look for things, and you can make a personalized treatment for each patient, know exactly. But this knowledge is coming in now. I mean, this is just, we've been doing this, basically in large scale for the past 6-7 years, a little bit with the Ipilimumab before that. But it's now we're getting the big numbers of data and the information, and we are understanding more and more about the process. But we know that this circle, that's what does it. And we're knowing more and more how to manipulate it to make it running. So more and more patients will get effect from this. That's the short-term forecast. The long-term forecast is, it's much easier for this circle to do its job the smaller the tumor is. And we're now getting technology that can identify cancer before you can see any tumor on any kind of imaging. You can take a blood sample and you can say, yes, this patient will get the cancer growing in their body in 2 years from now, with great certainty. Pretty much the same way as if you operate a melanoma patient in the first place. They have just a mole, you remove the mole and you leave a little more skin, and there is absolutely no more tumor and more known cancer cells in their body. You can take a blood sample and you can look for tumor DNA in the blood sample. And if they're tumor DNA positive in their blood samples, they are the ones that will relapse. The same in colon cancer. You remove the cancer, lymph nodes are okay, you don't find any cancer anywhere. Some of these patients have no tumor DNA in their blood samples, they never relapse. Other ones have tumor DNA in their blood samples, and they will relapse. The new treatment that will come in is that we're going to be much better at picking people up, both in an adjuvant setting, a secondary prevention when people had their tumor removed, and also in primary, where you know that certain mutations, certain genetic dispositions like that, you will follow these people and you will take blood samples and look for tumor DNA and other markers that they will develop a tumor in 1 or 2, and you can nick the tumor before it even starts growing. And that's the long-term future, and this is coming. I'm presenting pretty good news to you, right? And then, in that setting, my company comes in also. What we are doing, I showed you that we have antigens that we can present to the dendritic cells and get lots of T cells activated. And we can combine that with Ipilimumab or PD-1, PD-L1 blockers. But our vaccine can also be used as a preventive cancer vaccine. And we will develop it for being used for those very high risk with documented tumor DNA circulating in the blood. And we have a cooperation with NCI, National Cancer Institute in the US, and we're doing the development together with them. They have done animal models with our vaccine and testing, and we're starting discussions now and pushing this forward into the clinic. Okay, I have now 6 minutes left, and then I'll talk about my company. What we did was, in year 2000, started a clinical trial with the first version of our vaccine and gave it to lung cancer patients, and we got this survival curve. The blue line here are the patients that didn't respond to the vaccine. Nothing happened. They got no T cells activated against the peptides in the vaccine. Red one here is like this, and you see here, a little below 20% were alive after 8.2 years, and I can tell you they are still alive after 17 years. So these were long-term survivors. So what we did is we looked at the blood samples from these patients and compared it to these patients, saying, is there any type of immune response that correlates to long-term survival? And we found that. If the patients had immune response towards certain peptides, they would live for a long time. So we took those peptides and put it in the vaccine. So basically what we're trying to do is to mimic the immune response of these patients. And then, I'll just go straight to here. We have finalized 3 clinical trials, and these are the immune responses, number of patients that get response from the vaccine. Red line here is in non-small cell lung cancer, really sick patients. The blue line is in prostate cancer, not so sick patients, and they live longer. And the green one here is when we combine with ipilimumab. We go in and block up in the lymph node and let loose the T-cell clone expansion. And that's exactly what happens. They go up really quick and high. If you're really sharp, you will notice something, and that is that these lines don't start at 0. And they are the patients that had an endogenous immune response before they got the vaccine. They are the ones that didn't need the vaccine. They are the ones that would have responded to the checkpoint inhibitor on their own. Prostate cancer, clinical results. This is now close to 3 years observation of these patients. 9 of 22 patients have no signs of tumor left. They have stable PSA, and you can't find any kind of cancer, anywhere if you look at their blood samples or anything. Non-small cell lung cancer, 7 patients are alive out of 22 as of today, 18, sorry, as of today, and we have a median survival of 23.36, or 23 months, which is very good for these patient populations. So it's half of these patients, median survival is 2 years. And then comes the most promising. When we combine with ipilimumab, they have a normal response rate, around 20 to 30% of the patients respond. We add the vaccine. Now we have 18 months of observation on these patients, and we had 12 patients, and 9 of those 12 patients are still alive and they're stable, which means that 75% of the patients really did get a good effect of the treatment. So we'll follow them for a few more years and see, but it looks really good. The tumors are not growing, and they have stopped totally, 9 out of 12. And this is the cooperation that we have with NCI. And we didn't approach them. They came to us and asked for if we would give them vaccines so they could start testing it in their animal models. Okay, thank you.